Getting lost in weird new realms, understanding the universe's beginnings, the search of alien intelligence. These are the mission objectives of the James Webb Space Telescope, the long-awaited successor to the Hubble Space Telescope, not the narrative of the new science fiction film. Now that's NASA's new flagship observatory, the James Webb Space Telescope, JWST, is safely in orbit and nearly fully operational. It's worth looking at some of the cosmic secrets scientists hope to solve with the JWST. It will investigate two of the most mysterious questions in astronomy and cosmology today, among a list of high-priority targets. JWST is designed to scan the first stars and galaxies, far out in the cosmos and deep into the past. It will also aid in identifying exoplanets and the search for signs of life in the atmospheres of worlds orbiting other stars. It may also yield answers to some of cosmology's most esoteric concerns, such as how to better characterize the existence of dark matter and dark energy. Where do the dark matter and dark energy come from? Dark matter and dark energy are cosmic forces whose influence on the cosmos has been inferred. The revelation in 1998 that the universe is expanding and accelerating implies the existence of an unknown force or energy driving that expansion, which has been called dark energy. Similarly, dark matter is reduced from its effects on galaxies, which appear to be more massive than their apparent matter and energy would suggest. Dark matter is an enigmatic, invisible kind of substance that accounts for roughly 25% of the known cosmos. Despite making up a significant portion of the cosmos, it has escaped our understanding since Fritz Zwicky, a Swiss-American astronomer, originally proposed its existence in 1933. Dark matter has never been directly identified to date. Dark matter and dark energy are intriguing since they don't appear to interact with light or conventional matter. Yet they also appear to outnumber anything we can see. Scientists estimate that dark matter makes up 25% of the cosmos, and dark energy makes up 75%, leaving only 5% for everything else we can see. While the James Webb Space Telescope will not be able to directly see dark matter, scientists believe that by analyzing the effects it has on its surroundings, Webb will be able to answer several vital concerns concerning it. As a result, our understanding of the cosmos would vastly improve. Because you can't see dark matter, you have to walk around it in a roundabout method to see it. On the other hand, Webb can look at galaxies in new, orthogonal ways to try to figure out what's going on. Astronomers can, for example, use existing technologies to estimate how much mass is in stars and galaxies as a backdoor approach to detecting dark matter. Many galaxies could not exist or move as they do without a huge number of invisible material, which is one of the most compelling arguments for the existence of dark matter. Webb will take exceptionally crisp photos that researchers will be able to see disturbances induced by gravitational lensing, leading them to where the invisible mass is hidden to assist astronomers to more precisely locate that dark matter. While general relativity can be used to explain dark matter, it's lately become fashionable to try to explain dark energy by changing gravity instead. Dr. Claudia Durram's award-winning theoretical work has recently prompted The Guardian to inquire, has physicists' gravity theory solved impossible dark energy riddle? It's an intriguing prospect, but requires a healthy dose of skepticism. You can think of the universe as a race between two competitors: the original cosmic expansion, which causes distant things to recede from one another, and gravity, which attempts to recollapse the universe by pulling everything back together. The Big Bang is the starting point, and as distant objects start to recede from one another, gravity will kick in. The 3 points you can think of are comparable to the Goldilocks story. Either the expansion is too quick for gravity to halt or reverse, or the expansion is too fast for gravity to stop or reverse. Alternatively, there may be too much gravity for the original expansion rate to keep up, causing the expansion to slow, halt, or reverse, resulting in a big crunch. Or the expansion rate and gravity are perfectly balanced and our cosmic porridge is just right, with the expansion rate asymptotic to zero but never reversing. The universe, unfortunately for our intuition, performs none of these. If you look through the telescope at a faraway galaxy and measured its light from the beginning until now, you'd see that the light you saw was always redshifted compared to the light emitted. The fabric of space extends as light travels through the expanding universe. Its wavelength had lengthened when it reached our eyes, resulting in a redder color and lesser energy than when it was emitted. The faraway galaxy that first released that light is also getting farther and farther away as time passes. If there had been no dark energy, each galaxy would have a unique redshift, its light would be stretched by a certain amount that would gradually decrease over time. As gravity tried to decrease the pace of expansion, distant galaxies appeared to recede at a slower and slower rate, and their light became less and less redshifted as the universe evolved. Of course, the major question is why? Why is there dark energy in our universe? What is the significance of dark energy's non-zero value? And why does it possess the characteristics that it does? Dark energy has been incredibly consistent with what we will call a cosmological constant, one of the few things we can add into Einstein's general relativity theory, since it first alluded and then discovered in the 1900s from the large-scale structure of the universe, from the requirements of the universe's age for the stars within it, from the faintness of distant supernovae, and from the combined flatness of the universe with the measured matter density. The concept of cosmological constant is straightforward. The fabric of space contains a non-zero amount of energy. Modifying gravity has become hot recently, with numerous theorists experimenting with concepts that defy general relativity's principles. The most common sorts of changes either add an extra field, an extra set of terms, such as a new coupling, or they deviate from the idea gravity is the same rule for everyone at all times. General relativity has passed every test we've ever given it with flying colors. Therefore, all of these are already very confined. Some of these concepts, on the other hand, come and go. This fourth possibility violates Lorentz invariance, which entails abandoning the fundamental principles of relativity. A quick brainstorming question for you viewers. Is dark matter composed of ancient black holes? Let us know your views in the comments below. Lastly, what are the pitfalls of dark matter in energy research? JWST is designed as an infrared telescope for peeking into the past and far reaches of the cosmos, and a narrow field of view device for studying single objects in great detail. That's ideal for visualizing the universe's initial stars and examining the atmospheres of faraway worlds. Still, it's not the finest tool for researching dark matter and dark energy. Telescopes designed to explore dark energy attempt to observe a significant portion of the sky. We learn about it and assess it by adding up all the repercussions over an ample space or volume. It is undeniably true that dark energy exists. The evidence for its existence is overwhelming. While scientists can accurately describe dark energy, we still don't know what creates it or where it originates. It's possible that our current theory of gravity, general relativity, isn't entirely correct, and that the exact way in which it isn't correct causes dark energy. That's what the majority of modified gravity theorists are hoping for. However, this is still a little more than sandbox fun. Observable and quantifiable tests agree with general relativity in its unaltered form, and the value of the cosmological constant in all versions of gravity, modified and unmodified, remains an unsolved issue. The cosmological constant is an excellent source of dark energy. You can do the task differently if you choose, but be honest about what you're doing, adding an extra complication to something that is already complicated enough. With this, we come to the end of today's video. Don't forget to like, share, and subscribe to our channel. Do turn the bell notifications on so you never miss a video from us. See you next time.